A trained model is just a pile of bytes on disk. Every format that has ever existed is one answer to a single question. Who do those bytes belong to? Over a decade, the answer slid steadily rightward, from the framework that trained the model to nobody, to the compiler, and finally to the silicon itself. Machine learning model formats did not multiply for fun. Six pressures pushed them. Decouple the model from its training framework. Make sure a weight file can't run code when you open it. Load fast, map gigabytes instead of passing them. Stay portable across runtimes and chips. Get smaller through quantization, and at the end, go fast on one accelerator. Each format trades some of these against the others. In the beginning, the format was whatever the framework wrote. PyTorches.pt is a zip wrapping a pickle plus a raw tensor storage. TensorFlow's save model is a protobuf graph with a variables folder. Keras used HDF5. The upside is real. Save and load with no friction inside one stack. The cost, you're locked to that framework and Pickle hides a sharp edge. Here is the sharp edge. To load a pickle, torch.load opens the zip and hands the pickle to an unpickler, which walks an opcode stream. One opcode reduce can import and call any callable, so the file can run arbitrary code as it loads. It then rebuilds a state dict and copies tensors into the module. Because the file effectively is code, opening an untrusted checkpoint is running it. The fix is waits only equals true. Now the default, which permits only a safe set of types. The first real format invented to solve this problem was ONNX. Train in one framework, ship a single protobuf graph, nodes, weight initializers, and an offset version, and run it anywhere with an ONNX runtime. It broke framework lock-in. The catch, the offset is versioned, so conversion can drift and a model can use an op the target doesn't implement yet. Then the open weights wave hit, and the priorities became security and load speed. SafeTensors is the answer, and it is almost aggressively simple. 8 bytes of header length, a JSON header mapping each tensor name to its dtype, shape, and byte offsets, and then one contiguous buffer of tensor bytes. It is pure data and framework neutral. The trade, it holds weights only, not the model's architecture. So you still need the code that defines the network. Loading safe tensors is the opposite of executing a pickle. Read the first 8 bytes for the header length, parse the small JSON, and then map the file so the operating system maps its bytes to addresses. Each tensor is now just a zero-copy view, a slice into that mapping at its offset. Nothing is deserialized. The file already is the in-memory layout. Gigabytes are ready almost instantly and no code ever runs. As accelerators multiplied, a new problem appeared. N frameworks times M backends is a combinatorial mess of converters. The fix is a stable intermediate representation, an offset that everyone targets, turning the problem into N plus M. StableHLO and MLIR dialect is that boundary. PyTorch, JAX, and TensorFlow all lower into it. Crucially, it is not an artifact you run. It is the input to a compiler just like XLA. So loading a graph or an IR means building something runnable from it. parse the graph into memory, lower and fuse ops while folding constants, partition the work across CPU, GPU, and accelerators, then cogent kernels for the chosen target. Out comes an executable that is specific to the target and version. ONNX runtime does this on load. XLA does it ahead of time. Same shape because the bytes describe what to compute, not how. The compiler intermediate representation era has a second half the wait side often skips. The JAX and TPU world keeps its weights in ORBAC checkpoints. The parameters are a pi tree, a nested tree of named arrays, written sharded and asynchronously across many hosts. Because these models don't fit on one chip, it is the JAX side weights container pairing with StableHLO the way SafeTensors pair with model code. Same map verb, same need for the model code, and it is exactly what Google's GPU serving stack loads. At the other end of the spectrum is the laptop, GGUF, from the llama.cpp world. Packs everything into one blob, a magic header and version, a metadata section holding the tokenizer, chat template, hyperparameters, and the quantization type. Then per tensor info, then the tensor data itself. Quantization is baked in. You don't run a separate step. You simply pull the variant you want. GGUF loads by mapping, like SafeTensors, that adds two moves. After the mmap, the backend reads n GPU layers and splits the layers between CPU and GPU. Then, at compute time, each quantized block, 4 or 5 bits packed with scales, is dequantized on the fly into the math. The model is small enough to map on a laptop. The cost of compression is paid back in compute, one block at a time. The final binding is to the chip. TensorRT engines, NEFF for Inferentia and Trainium, Apple's CoreML, and LightRT for mobile are all terminal artifacts, already compiled and tuned for one piece of silicon. They deliver peak performance and in exchange give up all the portability. Move the file to a different chip or even a different runtime version and it simply won't load. Loading one of these chip-specific ML models is the simplest verb of all because the hard work already happened. A TensorRT engine is just deserialized back into an engine object. You create an execution context, bind input and output buffers on the device, and enqueue. There's no graph build, no auto-tuning, no compile. All of that was done at build time for this exact GPU architecture and library version. The bytes already are the runnable thing. So the whole zoo collapses into four verbs. Execute the bytes as a pickle does and as nothing safe should. Map them as safe tensors and GGUF do, the fast, safe default for weights. Compile them as ONNX and StableHLO do when the file is a graph. Or instantiate a precompiled blob as TensorRT does at the silicon. Where you put the binding decides everything else. Safety, load speed, portability, and who can run it. A model format is a contract about who owns the bytes. Chapter 1 ended with 4 ways to load one model. Production is a harder problem. Many models, many requests, all at once. The tempting hope is a single server that eats every format. It doesn't exist. And watching why splits the serving world cleanly in two. A generalist that runs almost anything, and a specialist built only for LLMs. Start with the reframe, asking, does this server support ONNX is the wrong question. A server doesn't run a format, it is a shell that hosts a runtime, and the runtime is what understands the bytes. ONNX runtime runs ONNX, the server just wraps it. So the real measure of any server is simple. Format coverage is runtime coverage. This is exactly how the broadest server works. Triton isn't one engine, it's a backend multiplexer. One front-end door for HTTP and gRPC with scheduling and dynamic batching fans out to many backends: TensorRT, ONNX Runtime, libtorch, TensorFlow, OpenVINO, FIL backend for tree models, VLLM backend, and a Python backend that can wrap anything else. It reaches a format only through a backend that runs it. One backend does outsized work: ONNX Runtime. PyTorch, TensorFlow, Paddle, scikit-learn all can be lowered into a single ONNX graph, and ONNX Runtime dispatches it across execution providers like CPU, CUDA, even TensorRT. So supports ONNX quietly means supports anything you can lower to ONNX, which is most of the classic model world. Convergence, not breadth, is what gives a generalist its reach. But the multiplexer hits a hard wall. CoreML, NEFF for Inferentia and Trienium, a compiled TPU executable, light-RT for mobile, each is bound to a runtime a general GPU server simply can't host. You can't multiplex an NEFF onto a non-neuron box. These are Chapter 1's instantiate artifacts, already compiled for one chip, and that's exactly where the universal server hope dies. Even within reach, LLMs broke the generalist's assumptions. A vision model is one shot, fixed input, fixed output, done. An LLM generates token by token, each step depending on every token before it, for an unpredictable number of steps. Pack such requests into a static batch, and the whole batch waits for the longest sequence. The shorter ones finish early and leave the GPU sitting idle. The deeper issue is memory. Every token caches its keys and values, so attention doesn't recompute the whole history each step. That KV cache grows with the sequence and quickly dominates GPU memory. The naive fix, reserve max length for every sequence, means most of the reserved space is never used. Memory, not compute, becomes the limit, and most of it is wasted to fragmentation. VLLM's answer borrows from operating systems. Page the cache. Split each sequence's KV cache into fixed size blocks, scatter them anywhere in GPU memory, and keep a small block table mapping logical blocks to physical ones, exactly like virtual memory. Fragmentation collapses, waste drops to near zero, and shared prefixes can even share blocks. This is paged attention, and it is why VLLM exists. The second move fixes the idle GPU. Instead of scheduling a whole batch and waiting, schedule per decoding step. The moment a sequence emits its end token, it's evicted, and a waiting request is admitted in its place. The batch is reshaped every step. Static batching leaves bubbles. Continuous batching keeps the GPU full, lifting throughput several fold without changing the model at all. Paged attention and continuous batching define a whole class of engine. VLLM, TensorRT LLM, SGLang, TGI, LM-deploy, and the Llama CPP lineage. They take SafeTensors in and GGUF for the Llama CPP branch and deliberately ignore everything else. Handing one of them a CoreML vision model is a category error. It solves a different problem on purpose. Inside that specialist world sits the fork from Chapter 1, GGUF. through llama.cpp and ollama targets the laptop. CPU plus GPU plus metal, one user at a time. Quantization baked into the file. SafeTensors through VLLM and TensorRT LLM targets the data center GPU. High concurrency, high throughput, paged attention. Same map verb from before. One mmap, two completely different destinations. So the landscape settles into two shapes. The generalist, Triton, Kserve, Torchserve, TF serving offers broad format reach through many backends, classic request response, ideal for vision, classification, embeddings, and tree models. The specialist, VLLM, TensorRT LLM, SGLang, TGI, offers deep throughput on safe tensors and GGUF with paged attention and token streaming. Pick the problem, then the server. One more split, the one this chapter quietly assumed away. Not every data center is NVIDIA. The GPU stack is safe tensors into VLLM or TensorRT LLM orchestrated by Triton or Dynamo. Google runs a parallel TPU stack, Orbax checkpoints into MaxText and Jetstream orchestrated by Pathways, a single controller spanning thousands of chips and the very stack that serves Gemini. Underneath, both run the same economics: paged KV cache, continuous batching, disaggregated prefill and decode. VLLM on TPU is where the two worlds are starting to meet. This is why nobody serious hunts for one binary that eats 20 extensions. The real strategy is convergence. Collapse many formats into a few runtime targets. ONNX runtime for classic and CV, TensorRT for peak GPU, and LLM engine for tokens at scale, and serve those. Standardize the frontend on StableHLO, then split at the end. Where you place that convergence point is the architecture decision. So the serving layer answers a different question than the format did. Chapter 1 asked, who owns the bytes? Framework, nobody, compiler, or silicon. Chapter 2 asks which runtime runs them, how many at once. A multiplexer hosts runtimes, not formats. The silicon locked blobs stay out of reach by design. KV cache economics forced a specialized engine, and the winning move is to converge, not to chase a server that does everything. Chapter 1 settled who owns the bytes. Chapter 2 which runtime runs them. This one is the question you actually face at the terminal. Which app do I launch? The trick is that an app is never a new kind of a thing. It is either an engine that runs the bytes or a wrapper that puts a face on an engine. And whichever it is, it inherits its format from the engine underneath it. Take the two you already know. Ollama is a wrapper. It pulls models and exposes an API and gives you a clean CLI. But it doesn't run anything itself. It sits on top of ollama.cpp, an engine that does the actual compute. So ollama.cpp is really one lineage, not two. Both speak GGUF because the wrapper can only ever speak what its engine speaks. Solid boxes are engines, dashed boxes are wrappers. This is the whole mechanic. A wrapper writes an engine, which writes a runtime, which understands exactly one family of formats. So an app can only run what that runtime understands. It is the same law as Chapter 2. Coverage is runtime coverage, which means the sprawling list of AI apps isn't a flat zoo at all. It sorts cleanly by format into a handful of clusters. Let's look at GGUF cluster. One engine, llama.cpp, sits under a crowd of wrappers. Ollama, LM Studio, Jan, GPT for all, Cobalt, CPP, local AI, text generation web UI, even llama file, which folds model and runtime into a single executable. Every one of them is dashed UX over the same engine, and every one is local, single user, CPU plus GPU, laptop class. The second cluster is where VLLM lives, and it's all engines, not wrappers. VLLM, SGLang, TensorRT LLM, Aphrodite, XLlama v3, the specialist fork from Chapter 2, built to saturate data center GPUs. One caveat worth carrying: TGI went into maintenance mode in late 2025, and Hugging Face now points you to VLLM or SGLang instead. Within that VLLM cluster, the choice is about workload shape. VLLM is a safe default, broad model support, paged attention. SGLang wins when requests share context. Its radix attention caches the shared prefix and runs roughly a third faster on chat, RAG, and agents. TensorRT LLM posts the fastest absolute numbers if you can stomach a compile step measured in tens of minutes. LM deploys TurboMind engine has the lowest time to first token on quantized int4. There is the TPU cluster the GPU world makes easy to forget. Google's own data center, which is TPU native top to bottom. The model is written in max text JAX. The engine is Jetstream, TPU native, and the same stack that serves Gemini. And orchestration is Pathways, a single controller spanning thousands of chips. It runs on GKE or Vertex AI over ORBAC checkpoints. The parallel is exact. Jetstream is to VLLM what Pathways is to Triton. A self-contained mirror of SafeTensors cluster, same economics, different silicon. ONNX cluster is quite the workhorse. ONNX runtime is the engine, and around it sit ONNX runtime Gen AI, transformers.js running models right in the browser, and Windows DirectML path. What makes it matter is reach in the other direction. This is where the broadest non-LLM coverage lives. Vision, audio, classifiers, embedding, exactly the models every LLM engine ignores. Now coming to on-device clusters, which are bound to the silicon. The chapter 1's wall, now wearing app names. LightRT with MediaPipe and LightRT-LM runs on phones and NPUs. CoreML and the increasingly preferred MLX runs on Apple Silicon. OpenVINO with OVMS targets Intel. TensorRT behind Triton targets NVIDIA. Each app is locked to its chip. That's the price of the performance. The cross-platform cluster refuses to pick a chip. MLC LLM uses a real compiler, TVM, to lower one model to web GPU, iOS, Android, Metal, and CUDA alike. And Web LLM runs an LLM inside a web page with no server at all. The idea is to compile once, run anywhere, the opposite bet from the silicon locked apps. Sitting across the top of all of this is the generalist tier: Triton, Kserve, TorchServe, TF Serving, RayServe, BentoML, Selden, and NVIDIA's newer Dynamo for disaggregated serving. The thing that makes them special is what they lack. They have no format of their own. They host the engines that do, format agnostic by design, exactly the multiplexer pattern from Chapter 2. Stand back, and the whole app layer is just four bands. Multiplexers on top, hosting the engines beneath them, engines, VLLM, llama.cpp, ONNX runtime that actually run the bytes, wrappers, dashed, that put a face on an engine, and at the base, the format and the silicon it's bound to. Every app you'll ever launch is one of these four bands, nothing else. So the choice is not a popularity contest, it's a lookup. A single user laptop wants Ollama or LM Studio. An enthusiast workstation, llama.cpp or X Llama v3. A multi-user serving box wants VLLM or SGLang. Production scale on NVIDIA, TensorRT LLM with Triton. And a non-LLM vision or audio model wants ONNX runtime or a generalist server. The workload class decides before any benchmark, which is the real shape of the whole trilogy, read as a chain. You don't start by choosing an app, you start with a workload. The workload implies a format that fits it. The format selects an engine that runs it, and the wrapper is just the face you happen to put on top. Pick the workload honestly, and everything downstream is nearly decided for you. Three chapters, one idea. Chapter 1, the format, is about who owns the bytes. Framework, nobody, compiler, or silicon. Chapter 2, serving, is about which runtime runs them and how many at once. Chapter 3, the app, is the engine or wrapper you actually launch, inheriting its format from below. Every layer, top to bottom, is a consequence of where the binding lives.